Hi everyone, this is Kiranmai from HNS department. Today we are going to have a session on dielectric and magnetic properties, unit 5 of applied physics, in which we are going to discuss about domain theory of ferromagnetism, hysteresis curve, hard and soft magnetic materials, and the applications of magnetic materials. First of all, coming to the domain theory of ferromagnetism, on the basis of hysteresis curve, we are going to have a session on ferromagnetic substances. In ferromagnetic substances, atoms, due to mutual interaction between them, they form innumerable number of small effective regions called as domains, where in each domain all the atoms will have a single direction. So when a ferromagnetic substance, when it is placed in external magnetic field, the magnetic moment increases by two different ways: one by the displacement of boundary, another by displacement of domains itself, by rotation of domains itself. So first of all, how the magnetic moment will increase due to displacement of boundaries of domains. See, when you place a substance in a magnetic field, the domains which are oriented favorable with respect to the applied field direction increase in size, while those oriented opposite to the external field reduce in size. The second option is by the rotation of domains. So this can be done only at the higher field intensity, higher applied field intensity. The domains rotate until their magnetic moment aligned more or less in the direction of external magnetic field. When the external magnetic field is weak, the substance is magnetized mostly by the boundary displacement. On the other hand, if the applied field intensity is high, the magnetation takes place by mostly by the rotation of domains. On the removal of external field, boundaries do not move completely back to their original position. Hence, the substance is not completely demagnetized. At higher temperatures, the domains break up and ferromagnetic substances become paramagnetic substances. On the screen, you can observe how a ferromagnetic material magnetic moment is increased with by application of less field and more field. Coming to the first figure, this is a ferromagnetic material which is having four domains which are aligned in four different directions: domain 1, domain 2, domain 3, and domain 4. Whereas in the second figure, second part of the figure, you are having the domains area is getting increased, which are aligned with the field direction. Let the field direction is from bottom to top. So whatever the domains which are in the field direction are making its space more by just displacing the domain boundaries. Whereas in the third part of the figure, you can observe that due to rotation of the domains into the field direction, the magnetic moment of the material is getting increased. This can be done only at the higher magnetic field intensity, higher applied magnetic field intensity, whereas second part can be happened at the lower magnetic field intensity itself. Coming to the hysteresis curve, consider one unmagnified magnified ferromagnetic substance in which is placed in a magnetic field. The substance shows a relation between magnetic flux density and the strength of the magnetic field applied. This property is called as hysteresis. How the material is getting magnetized depending upon the applied magnetic field. That relationship can be explained using hysteresis curve. When a substance is slowly magnetized, the flux density B increases with the applied field as a part of OA. That is, on the screen you can observe the part OA dotted line where you are just increasing the applied field intensity. Therefore, magnetic flux density is also increasing in response with the applied field intensity. So at a point A, the flux density becomes constant, that is the state of magnetic saturation, which means that as you are increasing the field intensity H, at some point called as A, the material is getting completely magnetized. Hence, there is no further magnetization in the material where B becomes constant. Such saturation is called as magnetic saturation. Now, consider the magnetizing field H is decreased. B also decreases but does not follow the path AO. It follows the path AB, which is in the as it is increased from origin to the point A saturation. If you decrease the magnetic field intensity, applied magnetic field intensity, instead of following the same path as it got increased, it will follow another path and it decreases to a point B instead of origin. So at point B, flux density has some value even if the applied field intensity is zero. The value of B for which H is equal to zero is called retentivity or residual magnetism. The magnetism which is left over in the material, even the applied magnetic field intensity is zero, is called as residual magnetism. Further, consider the direction of H is reversed. As H increases in reverse direction, B starts decreasing. The residual magnetism starts decreasing and becomes zero. The value of applied field for which residual magnetism is destroyed is called as coercivity. Coercivity or coercive field. Further increase of reverse applied field gives saturation point D. If now the field is increased in steps, the curve DEFA is obtained, and throughout the cycle, B lags behind H. Thus, lagging of magnetization behind magnetic field is called as hysteresis, and the path followed is called as hysteresis loop. On the graph, wherever you find that at any point B is lagging by H, therefore that lagging of magnetic flux density before magnetizing force is called as hysteresis, and the loop OA B C D E F A is called as hysteresis loop. Depending upon this hysteresis loop, magnetic materials got aggregated into two types: hard and soft magnetic materials. Hard magnetic materials are those which are difficult to magnetize and demagnetize, whereas soft magnetic materials are those which are easily magnetized and demagnetized. Hence, the hysteresis area will be large for the hard magnetic materials, whereas for these materials the hysteresis loop area will be very small for soft magnetic materials. Since this is easy, it is not easy to magnetize hard magnetic materials, so they need very high uh, applied field intensity to get magnetized. Hence, domain wall movement is difficult in hard magnetic materials, where domain wall movement is very easier in soft magnetic materials. So since these materials cannot be magnetized demagnetized easily, their coercive and retentive values will be very large for hard magnetic materials, whereas coercivity and retentivity are small for soft magnetic materials. Coming to the susceptibility and permeability values, that will be low for the hard magnetic material, whereas it will be high for the soft magnetic materials. The tungsten steel is the best example for hard magnetic materials, whereas iron silicon alloys are the best examples for the soft magnetic materials. Applications of hard materials will be like, since it is not easily magnetized and demagnetized, it will be used for compass needles, toys, permanent magnets, microphones, speed motors, and so. Whereas soft magnetic materials can be easily magnetized and demagnetized, hence they are used for transformer cores, motors, relays, sensors, storage components, and so many. So depending upon the area of the hysteresis curve covered, the material, it may be a hard magnetic material or soft magnetic material. If it is having high hysteresis loop area, then the material is a hard magnetic material. If the material is having low covering hysteresis loop area, then it is called as soft magnetic material. Coming to the applications of magnetic materials, soft magnetic materials, most of the time they will be used in transformer cores, motors, relays, and sensors. Iron silicon alloy magnets are used in electrical equipments. Silicon steel magnets are used in alternators and high frequency rotating materials. Soft magnetic materials are also used for storage components and microwave insulators. Hard magnetic materials are used in production of permanent magnets. Since these are not easily magnetized and demagnetized, these can be used as permanent magnets. Carbon steel magnets are used in toys, compass needles, meters, etc. Tungsten magnets are used in DC meters and measuring devices. Neodymium magnets are used in microphones. Cast alnico magnets are used in speed motors and sensors in automobiles. Microwave devices like isolators, circulator phase shifters are prepared from employing ferrites. Hard ferrites are used to make loudspeakers and wiper motors. Ferrite rods are used to make small antennas. And antiferromagnetic materials are used for coupling ferromagnets. And also these antiferromagnetic materials are used for coupling semiconductors also. And most of the examples like antiferromagnetic materials are also used for magnetic sensors. Ferrimagnetic materials are used as microwave devices due to low eddy currents. And hard magnetic ferrites are mainly used for permanent magnets. Production of cores for inductor coils is done using soft magnetic ferrites. And when ferrite rod is kept in varying magnetic field, it vibrates, which is used for the ultrasonic wave production. And ferrites are also used for thermal sensing switches, and these are also used for magnetic films. These are the certain applications of magnetic materials in different fields. Thank you.